Hi and welcome. So this is our 14th exploration of Sylow's theorem. Okay, let's set the alarm here. So, all right, alarm is set, people. All right. So yes, so this is our 14th video in our exploration of something called Sylow's theorem. Right. So this is 14th exploration, and we've really been thinking about this a lot. And the idea is, the claim is the following. Suppose we have a group G whose order is p to the alpha times m. Does that imply that we have some subgroup h of G such that order of h equals to p to the alpha, right? We're unsure about the truth of this statement. And so far we appear to have shown the following, that if order of G, if G is cyclic, we appear to have shown that if G is cyclic and order of G equals to p to the alpha times m, then this necessarily implies that there exists some subgroup h of G such that order of h equals to p to the alpha times m. So we appear to have proved this statement for the case when G is cyclic. And so naturally, what does that mean? Doesn't it mean that all we need to think about is the case when G is not cyclic? This is supposed to be an S, by the way. The case when G is not cyclic and order of G equals to p to the alpha times m. Well, does that also imply, or does that imply that there exists some subgroup h of G such that order of h equals to p to the alpha times m? Suppose we're able to prove this second implication. Would that imply that would that have completed our proof? Now, this is what we're evaluating before. The case when G is not cyclic but still has order p to the alpha times m. And we're wondering whether, well, does that necessarily mean that order of h has to be p to the alpha times m? So, I mean, realistically speaking, we're unsure. Right? We don't know yet. And the argument we're working on before was the following, that if we can prove this statement instead, that if G, of course P and M are relatively prime, if you can prove that when G is not cyclic, right, suppose we're able to prove this statement, if G is not cyclic and order of G equals to P to the alpha times M, and let's say from here we're able to guarantee that this means that there exists some subgroup H of G such that order of H equals to p to the alpha times L instead, where L is some divisor of M, okay? So suppose we're able to prove this. It looks similar to the one before, but there's a difference, isn't there? Like here, before we're just saying there's a subgroup of order p to the alpha times M. We're not sure about that. But can we prove that there is a subgroup of order p to the alpha times L, where L is just some divisor of M? Of course, if L equals to M, aren't we done? But suppose L is not equal to M. Suppose it's just a proper divisor of M. What do we do then, right? So the question is, suppose we're able to prove this, would we be done, right? Why would proving this statement here, let's call it 2 or segment 2 or something. Why would proving statement 2, right, amount to a completion of the proof? Why will showing that there's a subgroup of order p to the alpha times L guarantee us that we'll have a subgroup of order p to the alpha times M, is the question. So before we even try to establish whether this statement is true, whether statement 2 is true, let's first see if it's even worth our time. Does it give us a solution? Okay, does it actually prove that we have a subgroup of order p to the alpha? So let's think about that. Suppose that there exists some subgroup H of G such that order of H equals to p to the alpha times L. Okay, why is that useful information to us? is the question. Oh wait, well, we even talk of subgroups. Sorry. This is different. No. We want to prove this statement. We're not sure if it's helpful or not. Yeah. Suppose you have a subgroup of order p to the alpha times L. Why does that mean that we have another subgroup of order p to the alpha? That's unclear. Okay. So what if we proved this statement instead? So before we even try to establish it, it doesn't appear to be worth our while. Knowing that the order of h equals to p to the alpha times L does not seem to tell us much about whether there's a subgroup of order p to the alpha. So perhaps we can try something else. How about this? Suppose we're able to prove this instead, that if, let's call it statement 3, if order of g equals to p to the alpha times m, and g is not cyclic, then this necessarily implies that, yeah, suppose we prove this instead, that there exists some little g and g such that order of little g equals to p to the alpha times L, where L is a divisor of M, right? So this is different. It's not the order of a group, but we're saying there exists an element whose order is p to the alpha times L. So again, we don't know whether statement 3 is true, but suppose we're able to prove that it's true. Would this complete our proof? Does the fact that there is an element of order p to the alpha times L guarantee that there is a subgroup of order p to the alpha? Right? That's the question. So let's see. Suppose there is an element of order, suppose there exists some g in g such that order of g equals to p to the alpha times L. Okay? Can we say the following, that the subgroup, the cyclic subgroup generated by g, well, is going to be a subgroup of g, and in particular the order of little g is going to divide, sorry, the order of little g is, well, right, what's the order of little g going to be? Well, and they're going to be just p to the alpha times L elements, given that the element g generates our subgroup, and the subgroup, the generator g has order p to the alpha times L. Okay, so can we say then that our subgroup here has order p to the alpha times L? Okay, suppose that's true, so what? We came up with something before but completely forgotten what it was. This is an exploration without records. Well, there are records, but we don't look at them really. Sure, so suppose we found a cyclic subgroup of order p to the alpha times L. Yeah? Oh, yeah. So the thing is, can we find some h element of this cyclic subgroup G such that order of h is actually going to be p to the alpha, right? Because notice, if we have an element whose order is p to the alpha, right, aren't we saying then that h to the 0, h to the 1, all the way up till h to the p alpha minus 1, this cyclic subgroup is going to be a subgroup of G, little of this of the subset of the subgroup generated by little g, and it's also going to be a subgroup of the group. And what's the order of this this subgroup H? Well, isn't that just p to the alpha, right? So wouldn't we have found a subgroup of order p to the alpha? So the question becomes, how do we know we have some element that, how do we know that this H element of the subgroup generated by little g exists? That is, how do we know that the subgroup generated by little g has some element whose order is p to the alpha, right? And the idea here was, well, let's think about the element g to the L, okay? Well, remember L was just the order of the subgroup was p to the alpha times L. So g to the L is some natural number. So isn't g to the L an element of the cyclic subgroup generated by G? Okay. And what's the order of g to the L? Well, what's g to the L to the power of p to the alpha? Isn't that equal to g to the p to the alpha times L? But what's the order of little g? Isn't that 1? Isn't that p to the alpha times L? Right? Did we say that the order of little g was p to the alpha times L? If the order of little g is p to the alpha times L, aren't we saying that uh, g to the p to the alpha times L must give us the identity? Okay. Now question. Uh, is there some natural number n less than p to the alpha such that g to the L raised to the n equals to 1, right? Is there such a number, right? So please check that, please check and see if you agree that there isn't, right? Again, do not take our word for it. It's important to check for yourself. Check for yourself that there is no, see if you buy it actually, right? That there is no natural number less than p to the alpha such that g to the L to the n equals to 1, right? Okay. Now, so we've just found an element, little h, let's call this little h. If we said little h equals to g to the L, okay, haven't we just found an element h, element of the cyclic subgroup generated by little g, right? And we found that this element has order, what did we find? That this element has order p to the alpha. If this element has order p to the alpha, can we say the following, that the cyclic subgroup generated by little h has order p to the alpha, and that is a subgroup of the subgroup generated by little g, and this subgroup generated by little g is actually a subgroup of the group itself. So haven't we then found a subgroup, namely the subgroup generated by little h, which is a subgroup of g and has order p to the alpha, right? So do you buy the idea that if we can actually find an element little g of g whose order is p to the alpha times L, we're basically done, right? So, but again, this still begs the question, this is all nice and good, but how do we know? How do we know that we can always find an element that if g is not cyclic and the order of g is p to the alpha times m, how do we know we can always find an element whose order is p to the alpha times L? How would we go about proving such a statement is the question, right? And that's where we were led to study the properties of G, the properties of what it means for a group not to be cyclic, and what it means to have an order of p to the alpha times m, and Lagrange's theorem, which keeps telling us that the order of every subgroup must divide the order of the group. We're trying to use all of that information to see if it could be of value to us. So, okay, back to the black marker. So, how are we going to show that there's an element whose order is little g, whose order is p to the alpha times L, right, is the question. In what ways can we show this? So before we're on a trajectory, maybe it will help us. It's uncertain what's going to happen, but hence the exploration. Well, what do we know? That can we say the following, that for all little g in G, at least we know that since Lagrange's theorem seems to be telling us that the order of every element must divide the order of the group G, which in this case turns out to be p to the alpha times m, can we at least say that for all little g in G, right? Can we say that for all little g in G, it's actually true that well, order of G is always of the form p to the I times some L, where I is at most alpha, at least 0, and L is a divisor of M, right? Can we say that? Can we say that anything that divides p to the alpha times M is of the form p to the I times L, where p to the I is, well, some power of, where I is some power of p, which is less than alpha, at least 0, and L is just some divisor of M? Can you think of something that divides p to the alpha times M that's not in the form p to the I times L, right? Okay, if we can't think of such a divisor, now we somehow need to use this information to show us that, well, actually there is a divisor for which p to the I, the I is always alpha, and then we don't really worry about the L, right? So before we're trying contradiction, we are not sure the contradiction will work, but we hadn't completely eliminated it. So the idea was, let's suppose that the statement is not true. That is, suppose that actually there is no element of order p to the alpha times M, right? If we can obtain a contradiction then, then it means that there must be an element of order p to the alpha times L. I don't know if you buy this. So let's suppose instead, right, for contradiction, suppose that for all little g and g, suppose that order of G never equals to p to the alpha times L. Does never equals to p to the alpha times L, right, for any L divisor of M. So aren't we saying that this set here, let's call it B, the set B, which is p to the I times L, such that I is less than alpha, strictly less now, at most 0, at least 0, at most alpha minus 1, and L divisor of M, this set here that contains p to the I times L where I is less than alpha, isn't this set B, isn't it a set that contains the list of all possible orders that subgroups of, I mean, couldn't we say it's the set of all possible orders that elements of G can have, right? Let's see if you buy that. Well, Lagrange's theorem tells us that the order of every element must divide the order of the group. And given that the order of the group is p to the alpha times M, but the order of the group is p to the alpha times M, and given that the order of every element has to divide it, right? Aren't we saying that, well, first of all the order of every element of the group is of the form p to the I times L, okay? But what more are we saying? If we're saying that the order of the element can never equal to p to the alpha times L, well, and order of G divides p to the alpha times L, can order of G ever be bigger than p to the alpha times L? Can something bigger, if n is bigger than, if order of G is bigger than p to the alpha times L, how can order of G divide p to the alpha times L? Okay, so are we saying then that if we had to look at the list of all possible orders of elements of G, well, it's just a set B, p to the I times L, where I is strictly less than alpha? Hey, actually, is that true? Well, perhaps not. It's actually a little more complicated, isn't it? This is going to be an exclusive or, right? That is, if p to the I times L is the order of some element of the group, then either I is less than alpha, or, and this is an exclusive or, it's not like both of them can be true, exclusive, or only one is true, is what we're saying. Only one is true. Either I is less than alpha, or L is, right, or we know that L is a divisor of M already. Or L is less than M. That's what we're saying. That is, B is the set of all possible, is a set of pi to the L such that, well, either I is less than alpha, or, right, if I is not less than alpha, then definitely L has to be less than M, and L here is being taken to be a divisor of M. So this set here, could we say that it consists of all the possible orders that subsets, that elements of G can have? It's also, can we also say that it's a set of all possible orders of subgroups of G? Okay, so what? How does this lead us to a contradiction is the question. If it doesn't lead us to a contradiction, how can we decide whether or not to abandon it and try something else, right? So either it helps us or we give a justification for why it... Alright, well, okay, we just run out of time, so we're just going to continue from this part in the next video.